Okay, so this is still topic 2. This is the third and last video for this topic. We're going to pick up right where we left off, which is after example 10. And we're now going to discuss something called the dot product, okay? So what we can do is the dot product shouldn't be something new. You should have learned about this in calculus, but I'm going to show you how we can use the dot product to help us solve for vectors and forces, okay? So basically, the way we would pronounce this, if you guys don't remember, is when you see this A, little dot, and B, we just say A dot B. And the definition of the dot product is AB cos theta. And of course, this is if A and B are both vectors, and the angle between B and A is theta, okay? Now, I have this mathematical formulation here of what the dot product is for these Cartesian vectors. And basically all of this simplifies to our AX component times our BX component, our AY component times our BY component, and our AZ component times our BZ component. Okay, so all of this math just simplifies to this for each direction. One thing I want to note here is dot products are scalar. They give you a scalar quantity, which means that if you look at what's happening here, all of these are just single numbers, quantities being added together. So we're going to just end up with one number. It will not give us a direction. Okay, so the idea is, I'll show you in a couple of slides, we need to figure out if we're going to use the dot product to multiply vectors, how can we figure out the direction? And the way that we're going to do that is we're going to use the unit vector in some cases, okay? So we'll talk a little bit more about that. We can also get a direction between them using this theta. So let's continue here. We have two main applications of the dot product in statics. So the first is finding the angle between two vectors or lines, which was where we would kind of use this equation, A dot B equals AB cosine theta. And if we were to rearrange what's happening here, we basically get A dot B, which is the dot product, and then we would get this magnitude of the dot product here, and then we'd take the inverse cosine of that, and we'd be able to solve for our angle that that exists between both of those vectors that we're multiplying, okay? And the second application, not sure why there's an extra page here. Oh, okay, this page should have been here, so I'm gonna kind of skip back a little bit, but the second application of the dot product is going to be finding the components of a vector parallel and perpendicular to a line, which we're going to do in example 13. But before we do that, I'm going to talk about this a little bit and give you guys a couple of formulas that we can use when we're solving for this. So let's say we have two vectors. I'm going to redraw the vectors that we used up in the previous couple slides, AB, and we have some theta here, okay? So I'm going to actually put these vectors on some line here. Actually, what I'm going to do, let me work with just one vector for a second. So I'm going to leave out B, and I'm just going to draw one vector A here. And I'm going to draw some line here, and I'm going to call this line A. And what you guys can see is I can put this A vector into two components here. I can say I have this A vector, a component of it that acts along AA. These are all vectors. AA, which is equal to A cosine theta, this is theta, times the unit vector along A. What's the unit vector? It's the vector that acts in the direction here with a magnitude of 1. Okay? And I can also define a perpendicular vector. And I'm going to just reference this as A perpendicular. Okay? So it is 90 degrees from that line AA. Okay? And what happens here is the component of vector A parallel or collinear to AA. So here, that would be this guy right here. This is the component, I'll write it down, of vector A parallel, which means acts parallel, or collinear, which means it acts on top of it, to line AA, is defined by this A sub A equals A cosine theta. Okay, so the magnitude is defined by A cosine theta. So let's forget that unit vector for a second. Okay, we sometimes call this the projection of A on AA. We sometimes call this a projection of A on AA, or I haven't put the dash, so I'll just leave it as line AA. Okay. Now, the direction of the line is specified by the unit vector. So how do we figure out the direction of the line? We specify it by the unit vector. So right? Remember, our unit vector has a magnitude of 1. That's the definition of a unit vector. So if my unit vector specifies the direction, I can find the magnitude of AA, right, by taking A cosine theta, okay, or I can multiply A dot UA. I can take the dot product. I can take the magnitude of A, the resultant force A, and multiply it by the unit vector. This is a formula I'm going to use. Okay, and what we call this is we call this the scalar projection of A, of that vector of force A, along a line, which here is AA, and it's determined from the dot product, okay? This is our scalar projection. So what is the vector? What is the vector AA? If I want to add in the direction, I would just take AA, and I would just directly multiply it in, not take the dot product, because remember the dot product gives me a scalar. I want a vector here. This is the vector now, okay? Now, this blank page should have been after this. So this is actually part 1. I'm going to move up here to part 2. So sorry for the switch. But now what I want to know, I'm going to copy this image actually. Now what I want to know is, what if I want to find the components of A? So if I want to find, sorry, not components. I've already found the parallel or collinear components. So let me come back here. I've already found this guy. I just wrote the formula down on the slide before this, right? But now what if I want to find A perpendicular? What if I want to solve for A perpendicular? Okay, which is basically the component perpendicular to AA. What do I do? So I know that A, this is my vector addition, is equal to A sub A plus A perpendicular, right? This is just like saying A plus B is equal to the resultant. So I can actually directly solve. I can say A perpendicular then has to be equal to A minus AA, minus the parallel projection. And I have 2 ways of solving for this. So I have 2 ways to solve. Okay. The first way is to determine theta from the dot product. And I would get theta is equal to cosine inverse of A dot UA, my scalar quantity here, divided by the magnitude of A. And I can solve here for A perpendicular as just A sine theta, right? It's just the sine. If I have theta, which is A cosine theta, I can solve for A perpendicular, which is A sine theta. Okay, that's one option. The second option is if we already know A sub A. Let's say we know A sub A. Then, actually, this is just your scalar component, right? We can use Pythagorean theorem. This is just a triangle, right? We can use Pythagorean theorem. And we can say that A perpendicular, the magnitude is equal to A squared minus the parallel projection squared. So these are the other formulas that we can use for these problems. So everything I've highlighted in green is probably something you should be familiar with. And I'm going to show you this application in example 11 right here. Okay, so example 11, what we have is we have a frame subjected to a horizontal force of 300 J, which means it acts on the positive Y, and it's purely in the Y. And we want to know what the magnitude of the components of the force parallel and perpendicular to member AB are. So this is member AB. I'm going to put, here's member AB, right? So the parallel or collinear force acting along that member, and I also want the perpendicular. So I'm just drawing a perpendicular and parallel axis right now. Okay, I'm going to call the projection, remember this is projection here, I'm just going to call this one FAB. This is that parallel or collinear force. And I'm going to call this one here the perpendicular one, because that's what it is. It's the F perpendicular. So I just want to take my F of 300J and I want to break it up into components along AB and perpendicular to AB. Okay, now let's remember the magnitude of component F along AB. So FAB, okay, is equal to the dot product of F and the unit vector, right? Okay, this unit vector defines the direction of AB. Okay, so the first thing I want to do is I want to figure out what that unit vector is. So unit vector, let me define my direction. I need the position vector for B divided by the magnitude of B, and I get 2I plus 6J plus 3K divided by square root of 2 squared plus 6 squared plus 3 squared, and I get, I'm going to write that down here, 0.286 in the I, plus 0.857 in the J, plus 0.429 in the K. So I now have my unit vector directed along AB, that component AB. Now I can actually solve for the magnitude of FAB, which is equal to F cosine theta, which is equal to F dot UB. Okay, so I'm just going to plug in now. What is F? It's 300 in the J direction. And I'm going to use the dot product here and put in my other vector. Okay, this is our first time doing the dot product, so I'm going to go through this a little slowly. What I want to do here, I'm going to write down here. I need to, so this is one side of the dot product. And this is the other side of the dot product. Right? See the little dot in the middle. Okay, so what I'm going to do, I'm going to start with the X component. So I'm going to multiply all of the X's in the red box times all of the X's in the pink box. So what are the X's in the red box? Nothing. No X's or I's in the red box. Okay, multiplied by 0.286. Okay, now the Y, and I'm going to add the Y's. The Y, I have a 300, and I have a 0.857, plus now the Z, or K. I have 0 times 0.429, and I end up with a scalar value of 257.1. You just multiply and add all those together. And that is in newtons. Okay, result is a scalar, and we know that we already know the direction of FAB. It's the same direction as the unit vector at B. So this is the scalar FAB. If I want the unit vector, if I want the vector FAB, all I have to do is multiply this FAB magnitude that I have times the unit vector at B. So I would get the 257.1 times 0.286 in the I, plus 0.857 in the J, plus 0.429 in the K, and I can now get my Cartesian vector formulation for FAB, which is 73.5 in the I, plus 220 in the J, plus 110 in the K, and this is all in newtons. Okay? Now I want to get my perpendicular component, right? So I'm going to go back and use that formula that I highlighted in green, which is F minus FAB, right? This is just that 2 force components is equal to the resultant. I just subtracted 1 over. And I get 300J minus 73.5 in the I plus 220 in the J plus 110 in the K. And I get 73.5 negative in the I plus 79.6 in the J minus 110 in the K, and this is all in newtons. Now my F perpendicular is equal to the square root of F squared minus FAB squared. This is using Pythagorean theorem, and I get 300 squared minus 257.1 squared, and I can also get the magnitude of this by saying this is 155 newtons. Okay, so this is the last video for topic 2, and we've just solved example 11. So that's it for this video.